We're continuing our journey on multivariable calculus, physics. Today we're going to be looking at the Dell operator. So there are three ways you can take the divergence of the electric field. You can do it in Cartesian coordinates, you can do it in cylindrical coordinates, or you could do it in spherical coordinates. So 1, 2, or 3. The one we've been working on was this right here, where we take the electric field as a partial derivative with respect to x, y, and z, and you can figure out what the divergence of that's going to be. What we're going to look at later today is this equation right here, except it's going to be really easy. It looks long, but it's actually going to be pretty easy for the questions we're going to do. And it's the same thing for this. From symmetry, stuff's going to cancel out, and it's going to be an actually pretty easy equation to do. So there it is. And so if you're looking at cylindrical coordinates, you think about a cylinder. So what is a cylinder? A cylinder, let's say I'm the z-axis right here. A cylinder goes out radially, then it goes up in the z direction. So let's try that again. So I'm the center right here. This is the radius r. It's the distance from the axis of rotation. And then we can go up in the z direction. So we're right here. But then we can rotate like this. And that is the angle phi that we're rotating. So we move in the radial direction, in the z direction, and then we can move an angle phi. Okay? Now in spherical coordinates, we can do the same thing, except it's going to be a little bit different. So this is how spherical coordinates look like. I'm the center again. I'm the origin. So first I need a radius to go, whoop, there's my radius. And now, instead of going up, straight up like that, what I'm going to do is I'm going to make an angle like this. That's going to be my theta angle right there. I believe it's also called the azimuthal angle. So we go out this way, some radial direction, and then we go up like this at some angle. You see how I'm forming that angle? And then we can form another angle by turning like that. And that creates the spherical coordinate system that you have. All right? So you've got the Cartesian, the cylindrical, and the spherical coordinate system. Well, let's look at some of these. And it'll be easy. It's going to be, I think it's going to be easy. I don't know. The first case we'll look at is this, in the rectangular coordinate system. So, and it'll be a really easy question too. You've seen this before. It's just a point charge. So you have a positive point charge, and it's got a positive q value to it, and it's located a distance p from right here. And so we have an electric field. We know that goes in this direction right there. And you know that the electric field there is just k q over r squared, because it's just a point charge in the r hat direction. So that's the electric field there. We want to know what the divergence is. I forgot to put the epsilon here. Let's put that back there. We want to know what the divergence of this is equal to. So we just write down our formula. The divergence of the electric field is going to equal, now this is pretty straightforward. It's only moving in the x direction here. So we just have to write it as d dx. There's no y component to the electric field. There's no z component. It's only in the x. And then we put the electric field inside our derivative, and that's going to be k q. And you have to be careful here. You don't want to call it r anymore. R is a general coordinate. We're actually moving along the x direction, so it's x squared. And so there's your divergence right there. You take the derivative with respect to x, and you end up with, what is the derivative of this? It's negative 2kq over x cubed. And so that's the divergence. So what does this mean? What does this divergence mean right here? It tells us this is how much the electric field is decreasing by, the rate of the electric field, or the flux, or whatever you want to call it. This is how much it's decreasing by as a function of position, not time, as a function of position. So if I box this, P, if I were to box this P, and this was my point right here, we know the electric field is this big, but because it's a negative divergence, that means the electric field that came in to this little box has to be bigger than the electric field going out. And by how much is it changing by from here to here? It's changing by this much. That's what the divergence tells us. Okay? So that's a pretty simple question. I don't think it's too bad. Let's look at the spherical system. Where's my black? There it is. Actually, before we go to the spherical system, let's do one more in the rectangular coordinate system. And I have a picture for that. Here we go. There she is in all her glory. Take a second to write it down. If you want, I could even bring it down so you can see it a little bit better. Here we go. Take a second, freeze if you need to, and you have your picture. You have the electric field is equal to 5 minus 2x in the x hat direction, and in the y and z you don't have any electric field. So this is my 3D system here. I drew the y going back because we're looking at the xz plane, I guess. And the electric field is only moving in the x direction because there's only electric field in the x direction. Okay, and something else is it's a unit cube, so it's 1 by 1 by 1. And what we want to know is a few different things here. We want to know what the electric field here is, and we want to know what the electric field at x equals 1 is. So let's do that out. So to find the electric field at x equals 0, you just plug 0 into here. And so you get 5 minus 0, it's going to be 5 volts per meter. So that's going to be the electric field over there. And then if we wanted to find the electric field at x equals 1, we plug in 1 there, and we get 3 volts per meter. Now the flux is the next thing we want to find at each one of the points. So there's field lines going in and there's field lines going out. So what is the flux? Well, the flux is just the electric field times the cross-sectional area. So over here, it's going to be 5 multiplied by the cross-sectional area, which is going to be 1 meter squared. 1 times 1, that's the cross-sectional area. So the flux is equal to 5 volts per meter. And if we do the same thing over here, it's going to be 3 times 1 meter squared. It's going to be 3 volts per meter. Okay, so without going any further, you should have an idea of what the divergence is going to be, like positive, negative, or whatever. So the divergence of the electric field is going to be, well, if you're going from a higher flux to a lower flux, it has to be less than 0. Whatever the answer is, it has to be less than 0. So let's see if that's true. We'll do it over here. We can take the divergence of the electric field. And so to do that, you take the derivative of this with respect to x, the derivative of this with respect to y, the derivative of this with respect to z. Taking the derivative of this with respect to x, you will have, well, I'll just write it out, d dx of 5 minus 2 times x. And so that's going to equal -2. -2 volts per meter squared. All right. We get -2 volts per meter squared. Now, what does this -2 volts per meter squared mean? It means that for every 1 meter that I move, my flux is going to, or my electric field is going to drop by 2. So to go from here to here, for every 1 meter that I move this way, my electric field will drop by 2. That's what this is telling us. So the divergence tells us how fast the electric field is changing. Let me repeat that. The divergence is telling us how fast the electric field is changing as a function of position, not time. So there's another way we can do this, and it's actually a little bit easier, but it takes a little use to getting why this is true. We can say that here's your new equation for the flux, or the divergence. It's going to be the flux coming out minus the flux coming into the box. So this is going in, this is going out, divided by the volume of your object. So let's try that out. The flux going out is 3. The flux going in was 5. And all of this has the units of voltmeters. And then the volume is going to be 1 meter cubed, because it's this times this times this. It's a cube. So you do that, well, look at that. You end up with -2 volts per meter squared. So the divergence is telling us it's going to be the flux going out minus the flux going in divided by the volume between them. And that's equal to -2. Now you have to be careful with this equation right here. It's only going to work, I'm going to repeat this one time, it's only going to work if our cube is small. If our cube is very big, then it's not going to work out. And we'll see that in the next example here. So I'm going to erase this. Oh, one other thing, look at this. This is why it's actually important what I'm saying. This equation, you can't even see it. I got to bring it down. This right here, this equation is a linear equation. So as E increases proportional to X. So what I said before is true for linear equations. We're going to look at a nonlinear equation. We're going to do something similar and see what happens there in the nonlinear case. So in the nonlinear case, let me erase this. And we'll go up here a little bit. We're going to do, the electric field is going to equal parentheses 10 minus 2x squared in the x hat. And then the y hat is going to be 0, and the j hat or the z hat is going to be 0 as well. So this time it's a nonlinear equation here. So how do you solve the nonlinear equation? We're going to stick with our box that we have here. It's going to be 1 by 1 by 1. And when we do that, what we'll get is the electric field here. So if you plug in 0 into here, the electric field is just going to be 10 at x equals 0. And then the electric field at x equals 1 is going to equal, well, if I plug in 1 here, it's going to be 2. 10 times 10 minus 2 is 8. So it's going to be 8 over here at 1. And then we can figure out what the flux is going to be. It's going to be 10. And over here, it's going to be just 8. Oops. So this is the flux in. This is the flux out. Will be 8. And if you forgot, just remember the flux is just the electric field. The flux is just the electric field times the area. So the electric field times the cross-sectional area, which is 1, you get 10 and 8. All right. So if I use the equation I just showed you before, where it's the flux in minus the flux out, what we get is 8 minus 10 divided by 1 meter cubed, -2. So that is the divergence for this. Okay, sure, whatever. What happens if I do this, though? So I keep the same equation, except I'm going to change the box size. Instead of being 1 by 1 by 1, I'm going to call it a 2 meter by 2 meter by 2 meter box. Okay, so I got a 2 by 2 by 2. What's going to happen now? Well, the electric field at 0, x equals 0, is still 0, is still 10. So you plug in 0 into here, that's fine, whatever, we're good. Over here, though, the electric field at x equals 2, not 1 because we're a distance 2 now, it's a box by 2 by 2 by 2, is going to be 4, right? 4 times 6, and that'll be, no, 4 times 2 is 8. So 10 minus 2 is 2. So now the electric flux is 2. Sorry, it's 2 here. And the flux, this is where you got to be careful here. The flux going in is going to be 10 times the surface area. The surface area is no longer 1. It's a 2 by 2 matrix, a 2 by 2 by 2 cube. So the surface area will be 4. So you do 10 times 4, you get 40. That's the flux going in. The flux going out is going to be 2 times 4, and that's 8. So if we do the delta E just like we did before, whoops. If we do that, we're going to have 8 minus 40 divided by the volume. So the volume is going to be 2 by 2 by 2. So that's 8. Oh, did I say that wrong? No. This is for the first one. So this is for the second one. The volume is going to be 2 by 2 by 2, and that's 8 meters cubed. So what do we get when we equate that? It's going to be -4. So here we have a problem here. Over here, we got -4 if we increase the size of the box. Over here, we got -2. So why is there a discrepancy in the divergence? All I did was increase the box size. Isn't the flux that's going to go in going to be the same going out? And the answer is it's only going to be that if it's a straight linear equation. This is a nonlinear equation, which means that the flux going in, some of it could actually, instead of going out this way, could go out that way. So you're not going to get the same amount. And I guess the equivalent of me doing that would be something like this. Let's say you were taking the derivative, which is kind of what the divergence is. If you had a linear equation, and you had a line that was going like that, if you had a linear equation, you would just do rise over run. You would take this value and this value right here, and you would take the y, delta y, divided by delta x. And that would be fine. You know, we're good to go. And it doesn't matter where you go, the slope is going to be the same. But that's only true for linear equations. Now, if you have a nonlinear equation, like that, you know, there's a problem here. The slope here is not going to be the same as the slope here. You can't take a point that's right here and then do like a rise over run and take this value versus this value and say that that's going to be the rise divided by the run is going to be the slope for the entire thing. You can't do that. It doesn't work. You know that from calculus. So what you have to do instead is you have to look at a very small distance between them. And so when you take a small distance, then you can find the slope right there exactly. And if you take a point here, and you take the small distance delta x, you could find the slope right there. And that's exactly what we're doing here. So when you have a big box, you can't do this. That would be like going from here to here. So instead, you make the box tiny. You take delta, and you can make it smaller. And then in that tiny bit of box, the electric field is roughly constant. It's uniform. Okay? Now let's do our last two questions, and we're going to be finished. Our next equation is your favorite. You've done this so many times now, I don't even know what to tell you. So we have a charged, uniformly charged sphere. And I'm doing this because this is Gauss's law. The divergence of E is just Gauss's law. And let's see here. Here's point P. Point P is located right there. And we want to know what's happening there. We're going to make a blanket, a Gaussian blanket there. So there's a few things we can do. Let's see. What is it that we could do? We could write down our equation. That's a first. The divergence of the flux, or the electric field, is equal to rho times epsilon naught. So that's Gauss's law in differential form. Let's do this side first instead of doing this. So if we do this side first, we want to know what is rho. So what's rho going to be equal to? Well, rho is just equal to the total charge divided by the total volume. And let's call this distance little r, and we'll call this distance big R. So it'll be 4/3 pi big R cubed. That's what rho is equal to. And so we can solve for Q here. Q is going to be equal to, no. We're going to solve for rho still. So I'll just clean this up a little bit. I'll bring the 3 to the top right there, and you get rho is equal to 3Q over 4 pi R cubed. And so the last thing we need to do is divide by epsilon, because we're trying to solve for this term right here. So rho over epsilon naught is equal to 3Q over 4 pi epsilon naught R cubed. And if you want, we could simplify it and write as 3KQ over R cubed. So that's 1 over 4 pi epsilon naught is K, if you forgot that. So that's what this side of the equation is equal to. It's equal to that right there. I'm going to erase all this now. We don't need this. And so I'll just make a little marker here, and we'll say that that's what that's equal to. Okay. Now we got to do this side. So to do this, we need to first figure out what the electric field is equal to. How do you find the electric field? The electric field is just Gauss's law, E times dA over Q enclosed times epsilon naught. And so I'll save you the trouble and just work it out. We get 4 pi R squared on this side, and over on this side, it's going to be Q enclosed. How do you find Q enclosed? Q enclosed, you do Q enclosed over the total Q is equal to 4/3 pi little r cubed divided by 4/3 pi big R cubed. And the 4/3 pi's go away, and you're left with Q enclosed, which is equal to, we'll write it as Q over epsilon naught, and then the R cubed divided by big R cubed, like that. And then you bring the 4 pi R squared to the other side, and we get the electric field is equal to 4 pi epsilon naught becomes K, the R cubed, and that goes away, and you get Q or KQ times R divided by R cubed. So the K is just 1 over 4 pi epsilon naught. Now that we have the electric field, we can take the divergence of it. And so the divergence, the divergence of the electric field, here's where it's going to be interesting. We're going to use the spherical system. So in the spherical system, we are only interested, I don't know if you're even paying attention anymore, but I'll still try. In the spherical system, the electric field only depends on how far you are. It doesn't depend on the angle. So if you have a charged sphere, right? If this is a charged sphere, you just got to figure out how far away from the center of that charged sphere you are. It doesn't matter if you go up like this or like that or like this. It doesn't matter. It only depends on the distance r. So when you're here, the electric field, the magnitude of the electric field here is the same as if I go and now move it up an angle, and I move it up an angle like that. So what we can say is that in the spherical coordinate system, theta and phi don't matter. We just have to look at r. And I'll write down what the spherical coordinate system is just with respect to r. That's equal to, what is it? 1 over r squared d dr of r squared, the electric field as a function of r. And this is the electric field as a function of r. So all the other terms, that sine theta that you saw in the beginning, don't worry about it. It only depends on r here. Just like when we did in the first question, the y and the z there was no component in the y or z, so we ignored it. It's the same thing with this. So all you got to do is plug into this equation here. You get 1 over r squared d dr of r squared, and the electric field is kq r over r cubed, like that. And then anything that's a constant here can get pulled out. So the kq and the r cubed gets pulled out. You have kq over r cubed. You still have this r squared term on the outside. And we take the differential, the partial differential of r cubed here, because it's r squared and then the r right there. So the derivative of this is going to be 3r squared, I think. Am I right? Yeah, I think I'm right there. So we get 3 times kq r squared on the top, and on the bottom we have r cubed r squared, and the r squares cancel out, and look at this. You get 3kq r cubed, which is what we got on the other side of the equation. So when we took this side of the equation, we got 3kq over r cubed. When we evaluated this side, we end up with 3kq over r cubed. So either way, they work out to be the same value. And that's how you do that. All right, last question at Bronx High School of Science. The last question at the Bronx High School of Science for 2020. We're going to look at the cylinder. I'll make a bigger one too. Where this is completely filled in. It's charged and it's completely filled in. Okay. And what I want to know, I guess I shouldn't draw it like that. I should draw it with like little lines, because this is going to be the Gaussian distance. I want to know at this point right here in this thing that's filled completely, at this point right here, I know the electric field is going radially outwards like that. And I want to know a bunch of different things. So what do? We need to write some other stuff down. This is the distance L. This distance from here to here is R. So our Gaussian shell has a cylinder the size of R. And is there anything else I want to say? I think that's it. Okay. So let's work it out. We're going to use the cylindrical coordinate system. And in the cylindrical coordinate system, the electric field here it's all going to be the same. So the Z component doesn't matter. It doesn't matter how much you turn. It's all the same electric field for a long cylinder. So we start with our divergence equation, and we're going to put it in cylindrical form, and that's going to be 1 over R d over dr. The electric, oops, should it be R? I think it's R. Not R squared, but R times the electric field at R, and that's it. The other parts of the cylindrical coordinate system are gone because they're not dependent. The only thing that this divergence depends on is how far you are from the cylinder. Okay, so then the question is, what is ER? ER, we can use our equation first. We need to know what the density is. The density is going to be Q enclosed over epsilon naught. Right, so Q enclosed over epsilon naught. And from here, we can say that Q enclosed is going to equal the density. Did I say that wrong? I think I said that wrong. Kane with her dang cat box thing. So it's going to be Q enclosed over the volume enclosed is what I wanted to say. There we go. So it's going to be Q enclosed over the volume, which is going to be, what's the volume of a sphere? It's pi little r squared times L, because we're looking at the volume enclosed. So there's that. And so Q enclosed, if we solve it out, is equal to rho times pi r squared L. There's that. And then we can use Gauss's law finally. This E times dA is equal to Q enclosed over epsilon naught, but Q enclosed is equal to this, and this is a cylinder, so it's going to be 2 pi RL on this side, and on this side it's going to be Q enclosed. What? It's sad that this will be the second to last week. No, today is the last day of this. There's no more teaching going on after this. Well, at least that I'm not going to put on Google Classroom. I'm going to keep doing this over again, but today will be the very last official Physics C stuff. Okay? Movies will continue, but that's not what we're interested in right now. We got this. I got to finish this question here. Q enclosed is equal to rho pi r squared L divided by epsilon naught. And then we solve. So what do we get for the electric field? The electric field is going to equal, and this is the electric field as a function of r, it's going to equal rho times r divided by 2 epsilon naught. That is the electric field as a function of r. And now that we have this, I'm going to plug it back into my divergence theorem for the electric field as a function of r. And we get, this is kind of nice how it works out. You get 1 over r d dr of the first r, and then the electric field as a function of r, which was this term right here. That's rho r over 2 epsilon naught, rho r over 2 epsilon naught. And then I'm going to erase some of this. We're almost done. This works out really nice. If you're moving ahead of me, you'll understand why. We can pull out the rho and the 2 epsilon naught. So we have rho over 2 times r on the outside, and the epsilon naught as well. 2 epsilon naught r comes out. And then we're just left with d dr, and you just have the r and the r, which becomes r squared. And the derivative of r squared is 2 times r. So you end up with rho times 2 times r over 2 epsilon naught r. And look at that. The r's cancel out, the 2's cancel out, and we get what we said the divergence theorem would be equal to. 2 rho over epsilon naught. So divergence theorem, which is this, is equal to that, and that's Gauss's law. So we're just proving that. And finally, that's it. That is it. No more. You are free. You're done with